to see that there was a different deposit environment. So we link this deposit environment to lithofacies, which have their own petrophysical properties that we will use in the basin simulation. And so in the Batonian, for example, we go from 1 layer to 7 layers with a different type of carbonate, for example, Comblanchen, Oolite Blanche, and Dalle Nacrée. Now that we have our basin that is ready, we coupled so ArcTem, the calculator of Themis flow, with Codaster. The objective is to integrate the tectonic and the fracturic events over the geological history of the basin to provide a 3D model representative of the present-day fluid pressures and stress conditions. So the basin history is defined by a sequence of geological events, as I said before. This is why we do the backstripping in order to have all the geological events. And the porosity so is linked directly to the depth, and the porosity evolve with the pressure of the different layers. And so we have a law of the evolution of porosity, of the effective stress linked to the porosity. And we use the Schneider law for that. So this is what we have in Basin code. And in the geomechanical code, in Codaster, we have something more complicated. We have an elastoplastic constitutive law that has been developed by Bruch at IFP. And it is equivalent to the Schneider's law in odometric conditions, but it will allow permeability enhancement through fracturing. And how the coupling works, so it's an iterative coupling between the basin and the geomechanical code applied to each geological event. So the basin simulator calculates the pressure, temperature, porosity, and so on. And he gives this information to the geomechanical code, to Codaster, that we calculate the effective stress, a new porosity. And if the mechanical porosity is close to the basin porosity, we go to the next event. If it's not good, we redo the event with new information for the basin of the stress that the layer is seeing. And here's the kind of results we can have. So there is a slice here of the basin. So we can have different type of variables simulated here. We can have the temperature, pressure, stress fields, porosity, permeability, and so on. And all these variables will help to well constrain the initial state before the CO2 injection. But we had a little problem with our case. In fact, the Paris Basin is too quiet in terms of geomechanical condition, in terms of tectonic history. So in order to highlight the benefits of our workflow, we have pimped a little the tectonic history of the basin. We have played with the radiate thickness, the seal efficiency and its heterogeneity, a little with its tectonic history, in order to have something more complex in terms of tectonic. And so this is here the result we have obtained. Here we can see the delta of the fluctuation pressure. So here is the square we want to focus on for the reservoir simulation, and here we are very far from the fluctuation. Yes.
Can I see your pointer?
Yeah. Oh, yeah. So here is a little square where we want to focus our attention, and we see that here we are really far from the fluctuation. But with our new tectonic history, we see that we are very closer to fluctuation. So we want to see what will happen if we inject CO2 in this case, and we will compare the two cases. So now we go to the reservoir simulation. And we have also a coupling between the reservoir simulation and Codaster, the geomechanical code. But this time it's not an iterative coupling, it's a one-way coupling we have. So we calculate with geoxim pressure, temperature, porosity, and so on. We give the delta pressure to the geomechanical code, and it will give us stress, shear, and so on. And the initial state, so for the reservoir simulation, will be the result from the coupled basin geomechanical modeling. And so the objective is to simulate different CO2 injection scenario and doing the risk assessment. That is to say, reservoir and caprock integrity, fault activation, ground deformation, and so Just a little word about the method here. We have seen that we had an elastoplastic law in the basin, which is based on a modified Cham-Clay model. For the reservoir, with the coupled reservoir geomechanical simulation, it's based on a Drucker-Prager criterion, which is consistent with the critical state line of the Cham-Clay model, but which is a simplification. And so what is the risk indicator here in the reservoir? So it's defined by the distance to the Drucker-Prager criterion, so to this line. So for the reservoir, we'll use an isotopic distance, which is an assumption, a simplified assumption. We say that only the pressure variation impact the effective stress without changing the deviatoric stress. So we say that only the injection of CO2, we create a delta of pressure in our reservoir, and this is the only contribution for the reservoir. And for the caprock, because there can be ground deformation due to the difference of pressure in the reservoir, we use there the orthogonal distance. And so here are the results we have obtained. So on the left for the reference case, and to the right, so the alternative scenario. Here we have the distance to failure at present day before injection. So here we are quite far from failure. Here we are closer. And after 50 years of injection, so we have the result. So just a little word about the scenario. We have only one well at the center of the square, and the flow is controlled by a limit pressure of 40 bars. And for the alternative geological scenario, in order to have exactly the same flux, we have extracted the flux from the scenario and put it in the alternative scenario in order to have exactly the same amount of CO2 in both scenarios. Okay, ça marche. And so you can see after 50 years of injection that there is really a difference of plume or pressure in both cases. We have an intrusion of pressure in the caprock. There is no CO2 in the caprock, but there is an intrusion of pressure that we don't see there. This is due to the diminution of permeability, the decrease of permeability we have done in the caprock in this case, and we see that the plume of pressure is all along the basin here and is more localized in the reference case. Now, if we look at the variation distance to failure with the reference case and the alternative scenario, so what we can see after 5 years of injection is that so we're really far from failure in this case, and we're really close to failure in this case, in the center of close to the well, in fact. And after 20 years of injection, there is no significant no significant difference in the reference scenario, but we have a fracture area now in our alternative scenario. And if we go to 50 years injection, again, no significant difference in the reference case, but now we have fracture a lot in our reference scenario, in our alternative scenario, sorry. And last word about the criterion for the failure criterion we use. So I just want to focus our attention on the difference we can have by using different failure criterion. When we use the Rankine criterion, which is based on the minimum effective stress, we see the evolution of the minimum effective stress in the alternative scenario from 1 year to 50 years. And we see that after 50 years, there is no failure. The failure is not reached. You see there is the minimum effective stress is there. There is no failure. But if we look at the Drucker-Prager criterion, you see there is a failure just after 20 years of injection at well position in the reservoir. So we have to be really careful of the criterion we choose to see if there is a failure in the system or not. So we conclude on that. And what are the takeaway messages of this presentation? So we have developed an integrated basin modeling workflow, which provide a 3D model representative of geological facies and present-day fluid pressures and stress condition. And all these variables, we help to initialize the reservoir simulation. And it will allow to simulate different CO2 injection scenario with risk assessment. So what are the results we have obtained for the Paris Basin? Is that for the reference model, which is kind of the reality we know, there is no risk of failure in the reservoir or the caprock layers if we inject the amount of CO2 we have injected in the simulation. But for the alternative scenario, even if there is a negligible variation in distance to failure observed in the caprock. I haven't shown you these results, but you have to have faith in me for that. There is a failure reached in the reservoir after 20 years of injection when using Drucker-Prager criterion. But we don't see this fracturation using Rankine criterion, which is based on minimum effective stress. So what are the conclusion of that? Is that we have to be sure of the geological scenario and the tectonic history we want to use on our basin scenario, on the history of our basin, in order to lead to a representative present-day stress state, which will initialize our simulation, our reservoir simulation. And we have to be careful also about the failure criterion we'll use in order to be relevant, because it can be critical for geomechanical risk assessment. And now what we want to do, so we want to, in order to have a consistent approach, we want to improve our coupling between the reservoir simulation and the geomechanical simulator, in order to have a really coupled reservoir geomechanical modeling. And we will also to apply this workflow to other basins and see the benefit of this work. And that's all for me. Thank you for your attention.